All right then, what we're going to do now is we're going to do what's called differentiation by first principles, and it's the starting point really of doing this mathematically properly. Let's get straight on with it. Right, what we're going to do to get started is we're going to think of our old school definition of gradient, change in y of a change in x. Let's just write that down. M equals delta y over delta x. Specifically what we're doing is we're going from one position to another, one coordinate to another, and we're seeing how it changes from going in between the two. So we could write it as y1 and y2, xy, x1 and x2, you know, like a pair of coordinates. So it's the difference between this pair of coordinates to that pair of coordinates. That's all we're doing. That's the definition of the gradient from what we're used to do. Now we're interested in this situation where we've got a function and we want the gradient function, we want the derivative. Well, how do we do that? I'm going to have to draw a little diagram. So let me do that. Okay, now here's our little function that we're going to look at. Imagine that we want to take the gradient at one little bit, right? What we saw in the last video was what we'd want to do was we want the gradient here. We'd take the tangent off of there. Okay, there's our tangent. This is what we want. We want the gradient of that tangent. The problem is that if we wanted that gradient at right that on that just that little tangent, we could draw it and then, you know, read some values off and it would be a horrible approximation. So what we're going to do instead is we get this point here and we choose another point that's on this original function, say up here. And then we do the change in y of it and change in y over change in x of this point. So we go, right, we go along and down. So we've gone from there to there. And we've gone from there to there. So that's our change in y. And our change in x is that to that. But you see, there's a problem with this, right? Because if I did that and then worked out that, you're not doing the gradient at this point here, you're actually doing the gradient of that line. And what was that line? I don't know, that's not even on it. So this is a problem. This is not what we want. So what we do, something a little bit sneaky. We're going to take this point, right? This point here, we're going to move it closer and closer to the place where we want the gradient. So if we then, instead of being there, we move to here. All right, look at that. We now have this line. This coordinate is much closer to the one where we want the gradient, and this line is now nearer to our tangent. And I mean nearer as in, it looks closer. You know, the gradient looks much there to there, is much nearer than there to there. But it's still not right. Now, just before I remove this, let's make sure you've had a good look at this. I need to remove this. So what we do now, this is a beautiful little bit of mathematics here, is we say we need that closer and closer and closer until essentially, right, it's down there. It's even closer, right, it's even closer until it is just the tangent line. The way that we do that is we say that our change in x, what we're going to do, instead of before that I said you go, you know, 1 in the x direction, we're now going to go a little step and we'll call that step h. We're going to go from x there to x plus h. This is just a sketch, by the way. It still doesn't look very accurate, but what we're going to do is going to be accurate. So we've gone from x to x plus h, which means our change in x is that gap there, and our corresponding one is changing y. Whew, it's getting messy. So what we're essentially doing is we're making a tiny change in x so that our line that we're actually making the gradient, measuring the gradient of or doing the gradient of is our tangent line. Good, right, that's amazing. What that means is that we can now do this, sort of. But there's a condition on what we do. It will only be the gradient of our tangent line if we make that h really small. Now I'll come back to that in a second. Right. Okay, I tidied up the graph a little bit. It was getting a little bit too messy. Now it looks good enough to use. What we have here, the old school version, is we're going from one value of y to the other value of y. According to this, we're gonna, if we read off, well, this is a function of x. The value of it at this point here is just whatever that value of x is. So we'll just write it as f of x. I don't know what it was. And then here, well, it's that function at whatever this value of x plus h was. So f of x plus h. So our y has gone from f of x to f of x plus h, which means our change in y is that makes total sense, doesn't it, right? And now we need to do our change in x. So our change in x is x plus h, because that's where we are, and then minus the h. We just took a little step h along, so it's just that the x and the minus x cancel. So what are we doing now? Right, we've got that over that, but there's one condition, right? There's one condition. I said this only works if h is really small. So what we do is we introduce a limit. So we've got the limit of all of this as h tends towards 0. Nice, nice. But there's one problem. It's not m, is it? It's f prime of x. It's the derivative. So I can't really mathematically write that. I just used it to come up with this kind of derivation of differentiation by first principles. So let's write it out properly. This is differentiation by first principles. Let's get rid of that old junk. This is it. This is what we do. Now, thankfully we don't do this every time. This is just when we want to prove something. As I'll show in a second, we come up with little rules when we do this. I'm going to struggle with space a little bit here, but I'm thinking 1, 2, 3 examples. Let's go. Let's go really basic. F of x equals x squared. If we want the derivative, we're going to have to do this. So we put the limit as h tends towards 0 of f of x plus h. So we're going to replace the x with x plus h. All right. And this is f prime of x. I can't fit that on there. Running out of space. So we've got this thing here, which is a bracket. Obviously, we're going to expand that. That's what we'd like to do. All right, now this is our f prime of x. It's all of this going on. But look, we've got an x squared there and a minus x squared. They cancel. And we're left with this, 2xh plus h squared all over x. Well, now we're going to cancel out some h's. That h cancels with that one, cancel with one of those. Here's what we get left with. So we have f prime of x is equal to the limit of 2xh plus h as h tends towards 0. If we make h really small, oh, that shouldn't be there. That's better. As we make h really small, this just approximates to 2x. It becomes 2x. So the derivative of x squared is 2x. That's the gradient function of x squared. Remember in the last sketching the derivative video, I said how the quadratic is a linear. The derivative of a quadratic is a straight linear line. Nice. Let's do another example. I'm pretty sure I'm going to run out of space, but we'll try another one. We'll just go basic. F of x equals x cubed. Let's do the same process again. Just to point out, it's really important that we have the limit as h tends towards 0. Otherwise, none of this is right. Okay, I ran out of space again. What we've got here is I expanded the x plus h cubed, our bracket. We've got the minus x cubed on the end again because it's just f of x. And then it's all over h. Now this little bit at the end is quite nice. Again, x cubed is going to cancel with that. Then we've got these h's, that h cancels with that one, cancels with one of those and one of those. So what we get left with, the limit of 3x squared plus 3xh plus h squared. Well, if h is going really small, then that term's going to disappear to 0. That's a nice way of writing it. You do an arrow through it, and at the end of the arrow is a 0. Same, that's going to go to 0. So what we get left with, 3x squared. That was a 2x. So 3x squared. Well, well, well. Isn't this nice? We could keep going, and we could keep doing this over and over again until we start recognizing patterns. But I'm going to leave those patterns until the next video. I just want to talk about differentiation by first principles. There's a few other things that we can do with it. Before I move on, I just want to make sure you got these. Right, I've run out of space really badly, so I'm going to sort this out. Right, I need to be brutal with this. Differentiation by first principles. We had some examples down there. We're going to do one more, a bit more of a tricky one. I'm not going to do really difficult ones. I'm going to stick in the realm of like polynomials right now. Yeah. Right, we've got a quadratic now. Nice, big, fat quadratic. So we're just going to put this into there. Everywhere where we see an x, we're going to replace it with x plus h to do this f of x plus h. And then for the minus f of x, we're just going to do minus f of x. Now remember, it's minus all of f of x. So I've put a bracket around all of that. What I'm going to do now is I'm going to expand these brackets. Now I'm going to start cancelling off some things. Because, look, we've got an x squared there. We've got a minus x squared there. We've got minus 3x there. Plus 3x minus 4 plus 4. Okay, we'll get left to that. Now we've got h on the bottom. I'm going to cancel that off with some things on the top. Ooh, there we go. Right. Whew. I can cancel the h off like that because what we get left with is only terms with h's on. If I had something like an x squared, I can't cancel the h's easily because you'd be left with this x squared over h. But it's worked out all okay. What we get left with is, oh, I'm a hypocrite. I've missed the lim as h tends towards 0. Whew, here we go. Right, we're left with 2x plus 3 plus h. I missed the h from there. As h goes towards 0, this h on the end is just going to disappear, which leaves us with 2x plus 3. So we went from this to 2x plus 3, and I really like that. That is good. So I'm going to erase all that, and I'm going to do two last things, which are pretty spectacular. It's not going to involve an actual equation like that, but it's going to involve the concept of functions. So let's make some room. I can taste chalk. Let's say we've got an equation which is y equals 3 times f of x. The f of x is just some function of x. I don't know what it is. We want to find the gradient of this. Now, just like we go from f to f prime, I'm going to write this as y prime. And that's the limit h tends to 0 of okay, right? We don't know what f of x plus h is because I don't know what that function is. But look, f times x plus h minus 3 times f times x. There's a common factor of 3. We could just take out that 3. So the 3's there. The 3 doesn't depend on h, so we can actually put it on the other side of the limit. Ooh, and look at that. All of this, that's just the derivative of f of x. So it's 3 times f prime of x. So if you've got some constant, it doesn't have to just be 3. It's not 3's not a magic number. Some constant times a function, then all it is that constant times the derivative of that function. Nice. I like that. I like that a lot. So if we had, for example, earlier, I said that if f of x was x squared, then the derivative of that is 2x. Well, that was what we found out from first principles. What if it was 4 times that? Then it would just be 4 times, because it's 4 times some function of x. It's just going to be 4 times the derivative of that function of x. So it's just going to be 4 times that, 2x. So it's just 8x. Not bad. Not bad at all. That was one of the 2 things I wanted to say. Now let's have the second. I've written down what we just had as a little rule. If we've got a function and it's just some constant times a function of x, so if you could take out a factor of 3 or something, then your derivative is just that constant times the derivative of that function. That doesn't matter what that k is, any real number. That's quite hefty notation. But essentially, if you've got an equation, you can take out a factor of k, then all you need to do is that k times the derivative of that little function. It's fine, it's fine, you'll get it, you'll get it. Let me write something else. Okay, now we're interested in the situation where we've got y is equal to a function of x plus some other function of x. An example is, quite simply, if we had x squared plus 3x. We could look at that as one function, or we could say that's a function, that's also a function. So you can look at it as if it's the sum of 2 different separate functions. Cool. So let's go through the motions again. We're going to put this into there, y prime. So what I've done is I've just put x plus h into there, and then we're minusing just the normal one. So what we could do though is we could, because this is all over a common denominator, we could put this as 2 separate fractions. There we go. And as you might notice here, so the limit is of h tending towards 0 of all of that. Well, this bit is just f prime. This is just g prime. So what it means is if you've got a sum of 2 functions like that, you just find the derivative of each one, and job's a good one. Wow. All right. I know, actually, I like this. It might look like I'm pretending, to be shocked and everything, but this kind of stuff is great because you're often told that when you find the derivative of something where it's like, if it was x squared plus 3x, you just find the derivative of x squared, then add the derivative of the 3x. But it's never really clear as to why you can just do it to each one. Now this is just why. This is it. So I'm going to write this as one last rule, and then we're going to call it quits because differentiation by first principles is a bit techie. All right, it just is. So, right, here we go. I have rewritten this one in terms of y and y prime, just so it matches this one, of y and y prime. All this really means is that this is differentiation by first principles. You sometimes need it to prove things. So you might have to be like, prove that this is this by first principles. This is just an interesting property where if you can take out a factor, then you can just do the derivative of everything else and then put that factor back in at the end. This one is if you've got separate terms in an equation, you just do the derivative of each separate term and add them all together. And that's the derivative of something like that. What we'll do in the next video is something called the power rule, which is just from observing differentiation from first principles. You find rules, right? There's just patterns, and that's all we're going to do. So we get introduced to the very first pattern and how to use it. This is quite good though. What I would recommend that you do is to write a polynomial and have a go. Hell, you could even write something which wasn't a polynomial but was like x to the power of something. So try something like, actually I've kept it as a polynomial. Try something like that. Just see what you get. Right, that's it.